Hi everyone, thank you for coming. It's great to see you, some of you again, and maybe meet new faces. So today we are going to share kind of an annual report out on where we are on the OCP NIC area. And I've been doing this for, it's probably a 4th year or something, but we are making probably the most progress in the past year, so very excited to share with you. So this session we will have 3 Facebook engineers doing presentation, but I want to call out the work is really community work. Agenda, so I will give a probably 10-minute overview of the background, where we are, how we bring people to the same room, and how we work out something. And then Joshua and Yueming from Facebook will get more deep dive into mechanical solution and the thermal work being put into this spec. So first, a little bit background. So this is more like for the people like new to this topic. So where does OCP NIC come from? So initially, Facebook has a customized server with customized NIC, and the reason we do the customized NIC is trying to fit the NIC into a tight space that a PCIe card cannot fit. So I think that time, or maybe even now, many server system supplier does the same way because they want a compact form factor, and we were in the same place. So the difference is because Facebook was an OCP member, so we naturally contribute the spec into the OCP Foundation, but we didn't know what will happen after that. So fast forward for like a couple of years, in 2015-ish, we did a maintenance refresh for the specification. At that time, we migrated from 10 gig to 25 gig and higher bandwidth. And also, we added a PCIe connector, like one PCIe connector, increased from by 8 to by 16. So that was an incremental refresh, and it was also mainly led by Facebook. But by that time, we start to see interesting happen is if I wander around in this expo hall of OCP, I start to notice some motherboard like has a interesting cutoff and look like it's for OCP NIC. And I start also to see many NIC supplier adopting the NIC, although those NIC suppliers may not be Facebook's direct supplier. So we start to realize, oh, this spec is actually being adopted by non-Facebook supplier. It's probably for other people. And my takeaway is that there is a need for different company or different NIC and system company to have a common form factor, and OCP NIC happened to be the only one available in a fashion that people can accept. So that's kind of the background. But throughout the past 3 years-ish, I also started getting more questions saying, oh, I want to design OCP, my ASIC into OCP NIC, or I have a new use case. But somehow the 2.0 spec wasn't able to adopt that. A few areas such as the ball space and the mechanical and thermal profile limitation, and also the connector placement wasn't friendly for PCIe routing, as we have 2 connectors on opposite side of the car. And also the specification was also written in an incremental way, like the 2.0 spec is saying based on the 1.0, and here are the changes. So the readability wasn't great. So we get those feedback, and we take it really positively. We think that's a good chance for us to redo the specification, but we thought about doing it a different way. Instead of Facebook to write a spec and open up to everyone, and instead we think because there are a lot of adoption already by that time, and we think there are a lot of stakeholders there. So we want to involve the stakeholder and come out the specification together instead of having Facebook being the person working on it behind. All right. So on the timeline-wise, we started this effort around February last year. So the whole thing until now is spent around a year, and we're also looking forward for some more work to be put into this work till the end of the year. So initially, we start with setting up a subgroup with under the server work group with server work group's lead support. So we have the mailing list, the conference calls being set up, and the wiki. Initially, we set up conference call for like once a month, same as the server work group. And then exactly a year ago, we had the summit, and people start to meet each other face-to-face for the first time. And there were a few companies strongly recommend, say, if we need to make this thing work, let's do twice a month. So we changed the cadence of the kind of conference call. And we also set a certain time steps. So mainly, we want to start with just scoping the problem. Let's collect from everyone what kind of thing you see OCP 2.0 cannot fulfill, and what kind of design targets in terms of package size or thermal or use case you want to support. It's kind of a survey, but not guaranteed to be able to fulfill, but at least we get a good feeling of the requirement point of view from the community. And then we move into a stage of finding the options and eliminating option and the converge, and trying to build a spec, put more detailed work on one rough idea, which also takes time, and then going into the approval process. So I will get into a little bit more detail as a few examples, how we do each steps. So here is an example of how we define problem statements. So what we do is send out a survey, which include kind of what do you want the car look like, or what do you want the car support point of view. And we also divide the problem into a 90-10, like 90-10 means like you are very sure this is what do you want or what do you need, and 50-50 becomes a stretch goal. And then we just send out this spreadsheet to the mailing list, and I receive 5 returns. So in this case, we can put the data into a table and to see where is the commonality and which use case are more extreme, and where should we shooting for to capture, let's say, 80% of the use cases. And initially, the company was at that stage. That was about March last year. At that stage, the companies are pretty conservative, and I kind of play the game saying, if you don't want to get your name exposed, I'm just replacing your company name with A, B, C, D, E. So when we publish this, you don't know who is behind actually. But later, I see more open collaboration and the company directly working in the open space. And then another thing, then with the problem statement, we get into solution exploration. So one thing we do differently is although from my point of view, I get into discussion with some rough thoughts. Okay, I may have like 2 options. I see the pros and cons. But it's really important for everyone to get into discussion without a set agenda. Basically, we should be open to all options, even the option not on the table today, especially the option not in your pocket, like coming out from your pocket. You should be open to it. And let's just look at the pros and cons and make decision around it. Make sure everyone sees the pros and cons of every option. And easier, I think in community work, this is also important for the representative from each company to convince your internal peers, say why we make this decision, because here are all the pros and cons. So very interesting, we look at all, like from, we start with from like 6 or 7 different thoughts, and we end up exploring total 14 different enumeration or options of the implementation. We end up landing the last one and scrap all the previous concepts. But last one is the one that gained the most support. And throughout this discussion, also people see each other's momentum of willingness to take a change on both system and NIC side and throw away a lot of backward compatibility boundary. So then in September 25th last year, it's another, I feel like it's another milestone. So there happened to be an OCP workshop in Dallas, and that's also the first time people like have been working on the phone for a while get to meet each other. I also meet new faces such as HP at first time at that occasion, and I do feel like that is a good, there was a good forum for people really openly discuss. I start to see like maybe before that in each of the conference call, I'm pretty much So here's the agenda. After I go through, I may hear a couple of questions, but after that, I feel it's really interactive. The ball starts rolling by itself. And with a few months of work, we pretty much narrowed down to a solution. And today we have many actually. It's pretty amazing. We even have like 3 working samples around here. So I'm not getting into detail of like what it is part. Like you definitely can have a good look and feel of the difference between 2.0 and 3.0. But on top level, we kind of define a small and large form factor, and they actually interop to have the backward compatibility of each other. It's like if you have a system supporting a large form factor NIC, you can also stick into a smaller one. And also, I want to also call out the SFFTA 1002 connector is used in this specification. Thank T and Amphenol for the collaboration in the process. And this is also a connector being used by EDSFF and Gen Z, which we hope we will have a commodity of the connector in volume. And we also design in the EMI containment due to there are many OEMs are interested with this solution. And power envelope-wise, we have a much bigger power envelope from the power delivery point of view, although the thermal is another challenge that Yueming will get into. We put quite a lot of work into NIC management feature, and Hamel from Broadcom was leading the effort and put one section, I think section 4 of the whole management section, in a much more professional way than what I did in 2.0. So currently, from the we already submitted a draft to the OCP, and we are just wiping up the legal contribution process. So it should be an official spec shortly. So during this work, actually we just want to show some number here to show how many work everyone from a different company put into it. After I think around maybe August or September last year, we start to realize it's not enough to meet each other like 1 hour every 2 weeks. Instead, we start to host like every 2 weeks or sometimes every other week, a full day or half day of working session, and that's purely engineering talk. But it's really amazing to see people from NIC community like Broadcom and Mellanox and Intel work really closely, and also the connector guys working closely, and also system guys. Really, I feel like it's really a team. So, but we a lot of hard work. We had a 15 generic working session and also 11 mechanical specific working session. So over time, we have the trust so that we feel like we can run things in parallel and just report to each other to make it more efficient. Same thing for the thermal. And also, I want to kind of highlight Intel's effort. So Thomas from Intel took the lead on the documentation part, and there were total more than 40 versions. Today is maybe 50 versions that he cleaned up and posted to everyone. Yeah, here are the company that worked on it, and also there are more companies coming into this area. What I see like Keysight or University of New Hampshire and KVM are very actively engaged, although they are not in the list while we trying to wipe up the document, but I do see their contribution. So a little bit on the next steps. So initially we hit a milestone of 0.70 spec. So technically everyone agreed, and there are actually companies. We kind of get that point on end of January, and now, like after 2 months and a half, we actually have 3 companies already have working NIC sample bring to the stage. So I'm very amazed at how fast people move. And then I already put an end of February, but end of March, we probably should have another stage of the hot fixes. So we're already on 0.72 or something on the hot fix, but we will throw in some hot fix. The next stage will be 0.9, which will aid a signal integrity guideline, which is also a session on 2 o'clock today. It's a joint session from Facebook, Dell, and a few other companies talking about how to make the compliance work on the PCIe side. So it will be an important and interesting work to follow. Hopefully, we can, by end of the year, with the learning of the implementation on both system and NIC side, we can call the spec 1.0 as we have a few typical use cases proved to working, and the stable specification will be very stable after that. With that, I'm going to pass to Josh for the mechanical stuff.
Hi all, I'm the mechanical engineer, work for Facebook. I led the mechanical working group for this OCP NIC. So one thing that John didn't mention that's kind of interesting about the OCP NIC is that originally this was called MES 2.0. And when we came into this, option 14 ended up not being a MES at all. So I know you're all used to hearing MES 2.0, but now we're calling this a NIC 3.0 because it's not a MES anymore. So that's something that's interesting. Here are some differences between the new NIC as well as the current MES 2.0. The main thing is really a connector orientation. So in MES, this actually isn't a great example, but in MES 2.0, you actually had mezzanine connectors. So the action of installing this into a chassis was kind of like in through the top cover, and you made it into the motherboard. The one thing that's really problematic with this is the EMI containment, as well as just the overall configuration and not having access to it outside of the box. So when we started to talk more about doing the 3.0 spec, having something swappable seemed like something that would be interesting to a lot of people. So we ended up with a connector, gold fingers on the back of the card. And it's more of a, size-wise, it's slightly bigger. You can tell by the table here. But it's a little more organized, where in 2.0, we kind of had all these weird cutouts and different heights and all these things. One of the big things we want to do is simplify all that, make it a nice square rectangle that you could keep components in, and it would make it really easy to adopt and make changes. So those were some of the key differences between the two. Physically, they're about the same size. This one's obviously a little bit bigger. It does a lot more, though. So I did mention EMI containment. We do have fully engineered EMI containment on these. We haven't done testing, but the mechanicals are part of the spec. This was something that was always really difficult with this, was making elegant solutions to provide EMI containment in the chassis. So as part of the spec, we wanted to define mechanical containment as part of that spec to really lower the barriers for adoption and make it much more easier to implement. The overriding goal was to really get the NIC manufacturers to help provide a finished NIC out of a box that you can plug into a box with minimal engineering. So that's kind of one of the big goals we had with the program. This slide kind of goes through some of the components. This is kind of the chassis, looks like this. This is a right angle, but this is a straddle in this case. So we have the motherboard, we have the NIC, we have the SFF connector here. This is a special SFF connector with an optional OCP bay that gets added to just give us a proper pinout that we need for this. And we have some card guides. Really simple, very minimal component count. And you can also mount this in different orientations and all different sort of implementations. That was one of the things that the mechanical group really focused on, was all the different goals that we wanted to achieve with this, because we had all kind of had similar experience with 2.0, implementing 2.0 into our chassis. So we wanted to try to build on that experience and bake it into 3.0. So these were some of the mechanical goals. The overriding one was develop a universal form factor that should include EMI containment. This was something that everybody could easily agree with. Some of these other things, this is along the list. I won't go through every single one, but we really wanted to make it so anytime you make a change, it's a minimal change. You're changing a number of ports, or slight configuration changes. You're moving a connector, you're adding LEDs, things like that. We also wanted to produce really good 3D reference CAD that somebody could start with, right? Something really solid, a solid base to start with, just so you're not having to engineer that every time. We also try to really leverage a lot of the design items between the small and large form factor. So as part of 3.0, we also wanted to define a large form factor. This is what we call the large form factor. It's quite a bit larger. But the mechanicals leverage a lot of the same elements from the small form factor to the large form factor. Again, providing some consistency across the spec to really make it easy to make changes. So all the mechanical items like, oh, it has, the small form factor has this latch. Well, in some cases, the latch is exactly the same on the large form factor, but all the overriding geometry in this area is all the same. All the hole placement's the same. All the hardware is the same. So this was something we were trying to do, really keep it really, really simple. And I think we've achieved that. So let's move on to kind of the overall configuration. I've already touched on some of these, obviously. So this does have increased PCB space over the 2.0. It has really simplified component key-pin areas. So on the top, we have an 11.5 millimeters height, and it's basically a rectangular box, a key-pin box on the top. On the bottom, it's kind of a key-pin box. It's a little more complex because we have this insulator on the bottom, but we have 2 millimeters on the bottom of total height. And thanks to the NIC manufacturers, they enabled us to go to those very low heights that the system vendors had wanted. Other things, again, built-in EMI containment. We have EMI fingers top and bottom, as well as side and side. Some very small fingers on the side. So this should hopefully make it very easy to pass tests right out of the box. We have it available in a thumb screw version as well as a latch version. So one unique thing that we wanted to do is, so thanks Intel, they built these PCBs. These are functional PCBs. The PCBAs are actually the exact same between these two assemblies. The only difference are the mechanicals. So you can easily bolt one onto the other or vice versa. So the idea there is that we can provide a lot of different versions to the community with no impact to the PCB. It affects qualifications and all those sorts of things. So hopefully within one PCBA, you can get the alternate mechanical fixings that you need for your box. Module size. So this module is 76 by 115. So the total width, obviously 76, 115 is the length. The large form factor, it's just a lot wider. What we do is, in the large form factor, this has what we call a 4C. This is a 4C with OCP bay sliver connector. And this actually has the exact same connector in that position, right? And then we add an additional 4C in the rightmost. So that grows the card to 139 by 115. So it's quite a bit bigger for big FPGAs, big heat sinks, higher power cards. I won't go through the specifics here. You guys can look at the deck. So these are some of the variants. Again, I mentioned we have a pull tab version as well as a latch version. These variants, we developed these variants because different system manufacturers really want different things. At Facebook, we like everything toolless. Other vendors really want to have some sort of thumb screw, so you need a tool to remove it. So we ended up with these two variants. This is the 3D CAD that's actually available on the website. And that's the 3D CAD that was used to build all the samples you see down here, including the working units. The ones on the left are all pull tab versions. We typically do the mechanical designs based on the worst case connector configurations. That's why you see 4x and not 2x, because you can easily scale that down to a 2x. You just close that hole up and you have your 2x. And then here on the right, we have the toolless versions. Again, the PCBAs are all the same. You can get the CAD there. So here's our large form factor. There's actually been a change since the slide deck. The original plan of record was this 2 ejector system here. And after I prototyped it, I didn't really like it too much. So we're really trying to go to a single ejector for this large form factor. But this just kind of shows you the available space on something like this. It's a very large card. We also have 2 chassis variants as well. We have on the left, well, it's kind of hard to say. On the top, we have our straddle case, which basically means that the NIC PCB is on the center line of the motherboard center line, so there's a cutout in the motherboard, right? So the straddle is below. The right angle, the NIC actually exists above the motherboard, so you could physically route under that. But these are the two variants. One of the big overriding things we also want to do is have the flexibility with these two mounting variants to make this still the same thing, right? So it's a module. It can go into either a right angle slot or a straddle slot. It doesn't really matter. So with that, I'm going to give it over to Yo-Ming so she can handle the thermal. We do have about a few minutes between the next session and this session, so please come up and take a look at the mechanicals as well as the functioning units when Yo-Ming's done. Thank you very much.
Thank you, Josh. So afterwards, I'm going to talk a little bit more on the thermals for NIC 3.0. So basically, what's the difference between MAS 2.0 and our new NIC 3.0? The main difference, we see a lot of thermal benefits over this. As Josh just mentioned, we have gone through 14 different options, and each option we kind of also evaluate what does it mean to the thermal. And by comparison, the main benefits I list over here is 3 items going from MAS 2.0 to NIC 3.0. The main one, the number first, is that we have, since we get rid of the Berg stack connector on the side, so basically we give more space on the width perspective to the heatsink. Basically, that also gives us more capability of cooling higher power ASIC. And also another thing is that since MAS 2.0 is actually facing down, and so the heatsink height is actually limited by how high the Berg stack connector is. And then by facing up the NIC, we actually have more flexibility of growing the heatsink to even higher, to support even higher ASIC. And also another thing is that for the large form factor, since we kind of adopt both options, right? So small form factor, it's a compact model, and we can use it in some chassis which needs less space. However, if we want smart NIC and also higher power NIC, we can go to the large form factor. It gives us more space. We can grow the heatsink even bigger. So these are kind of the 3 main benefits from thermal perspective for the NIC 3.0. And next, we're going to talk about what is the actual thermal design guidance for the NIC 3.0. So during our communication efforts, a lot of people were talking about, oh, we don't have any thermal guidance. We don't know how we're gonna build the NIC 3.0, and we don't know what's the maximum power we can support. So that's why we go ahead and do all the CFD analysis to kind of find which is actually the power limitation that thermally can support under this envelope. So another thing I want to highlight over here is that the NIC 3.0 actually can go into 2 different kind of use cases. One is which we call front I/O. So basically, it means the cool air from the cold air just directly pass through the NIC and then goes through the GPU. And by the fans, they take it out of the chassis. And another scenario is that the hot air cases, which means that the NIC is actually on the back side of the server. So basically, it got shadowed by the CPU, by the hard drives, by all the components in front of the chassis. So we kind of do both. Because Facebook, we are kind of cold L use cases, but all the OEMs, they kind of looking more into the hot L. So we did both study. So from here, this is a cold L simulation data. So we kind of have in the chart on the right-hand side, we kind of have 3 different kind of zooms. The green one is a typical server L flow. We think it's it's a bare minimum, it's a minimum L flow we can support under a typical case. And then we have a higher fan speed region, which means that if the system can take the risk of operating the fan at a higher level, basically we can support even higher ASIC power. And also we have this red zoom, which means that it's not typical server use cases. So when you design the NIC, you probably need to take that into consideration. We do not put too much higher power to the NIC, so we cannot cool it. So basically, we choose 35C as a kind of typical inlet temperature to the NIC. And by doing all this like CFD simulation, we can see that under typical airflow range, we can support like 15 watt ASIC with no problem. And if we can like achieve more airflow through the chassis, we can support like 23 watt. And this is all based on our like kind of generic ASIC design. We use like extruded aluminum heatsink design. And if we go to copper, like accordingly, this power can scale up as well. So next is the hot L cases. Basically, since we have higher supply L temperature for the hot L cases, so basically it's more thermal challenging under this use cases. So we also choose a typical supply air temperature 55C over here. So for small factor, what we see is that we can support 15 watt. And the high fan speed version, we can probably support 20 watt. And also this is only for the small form factor. We're still like doing more investigation on the large form factor. And as Joshua just showed over here, we actually try to separate the kind of the I/O module to the side as well, trying to kind of, because for the hot L cases, the I/O module is actually shadowed by the ASIC, right? So we want to give more cool air to the I/O module itself. So that's why like we are still doing more analysis on the large form factor. But this is a guidance for the small form factor. We're going to add more for the large form factor when the next spec comes out. And last thing is that also during like the Dallas workshop for OCP NIC, a lot of like community members point out that, oh, we have the NIC, the NIC vendor have the NIC, the system vendor want to adopt the NIC. However, we don't have a common text fixture, so we cannot communicate data in a very clear way. So how about let's create some text fixture, which is a standardized way, so that people can communicate the data, and also they can kind of, it's like simple and also easy, adopt the data so that the system vendor can take whatever the NIC vendor using the standardized way, and then we can kind of analyze that data to see whether our chassis can support this NIC or not. So basically the three features over here is that it's simple and easy adopt, and also it can give the representative thermal data to define different tiers. What does tier means is that basically a NIC under certain inlet temperature, it might need certain airflow to cool it, right? So it kind of defines different layers. So which means that if your system, oh, I can only support up to certain tier, then basically I can choose all the tiers below that, so I can support that NICs as well. And also, Dell give a very good cooperation on this, is that we have the actual kind of text fixture mockup over here. So basically what it does is that it also have the functioning board on the inside of the chassis, which means that it can deliver power and also get the data recorded very easily. So thank you for John's effort on this. So this is all for thermal, and I think we still have a few minutes for questions, but after that, since we have a 15-minute break for the next session, so we have all these components laid out on the ground. So if you guys are interested, please come by and take a look. Thank you. Questions?
Oh, the question?
Yeah.
Okay. Oh, so the question from John is how do we release a spec from after post 0.7? So I think largely the working model will be still similar. Before we release a new spec, it's probably still for whoever willing and to put a time on it, we will still build a consensus before we put in the spec, put in the draft. We touched a little bit about this topic on the workshop call, or the call like earlier this month. We may set as like a major release every month. So around the kind of first week of the first Wednesday of every month, we hope to release a new version. And maybe 2 or 3 weeks before that, we may host a workshop to get into detail and agree on something, and take 2 weeks to draft it up, the change and the review, and then put it in release. And on the first Wednesday of the month, we may also take some new topics, maybe identify 2 or 3 items we want to work throughout the month. So from now to the end of the year, we should have this kind of cadence going forward to rolling into either hotfix or major improvements. And I know there is a few topics is going on talking about improvements. So I think it's also a good reminder for me to call out. As you see, there are already companies building NIC around it. Maybe there are some system suppliers thinking about doing system. So if you are thinking about taping out something or like getting to the design stage, please do work really closely with us so that you will follow up, and at least we will be able to communicate to you or include you in the discussion. What are the pending changes? What are the things that people are thinking about change, so you can be part of the decision process instead of being surprised by a change. I think it's extremely important once we go through 0.7 and people start to taping out stuff. So, yeah. Any other question we can take? Yeah, and also I think this is a chance for us to communicate to broader community, broader companies, other than the more than 10 companies we already work closely with. And one example is I get some question from, I think, Fujitsu yesterday, asking about some mechanical improvement. But we wish to see more of these kind of inquiries. So I want to encourage you, if you are not working with this group closely, please do reach out and at least meet and say hello. Yeah. All right. If no more question, I think we will just stop session here. But next session is on 2 p.m. sharp, right?
Yeah.
Yeah. So
another 15 minutes. But feel free to come up and talk to us and look.